Hello folks, this is Tom from anti-proton.com, and today I'm here to talk to you about radiation, but not really too much in depth. I just want to show you the 4 basic types of radiation most people bump into in their normal days, and show you examples with real radioactive material, because everyone just wants to see real radioactive material, right? Maybe you'll learn something on the side, maybe not, who knows. But let's get down to it. First off, let me show you the equipment that I'm going to be using. This is an SE International Inspector EXP Plus. It is a Geiger counter. How do we know? Because if we take the protective cover off, this is a Geiger-Müller tube. Geiger-Müller tube. See? This thin metal mesh around here in the front is protecting an even thinner mica window in the backside, which allows for things like alpha radiation to get through, and I'll show you in a minute why that's important. But this is the detector. We'll put this right here. Okay. It connects to this. This is the actual Inspector Geiger counter, and you see the 38? That means that there are currently 38 counts, well, 32 counts per minute is the average number of counts this is getting, and counts are the interactions between radiation and this. So when something radioactive passes through, tick, you get a tick. Make sense? This thing's giving me a running average. All right. Obviously, you can tell this by looking at it, that 20 and 30 and so on counts per minute is pretty much my standard background. Let me get this cable kind of out of the way. This little guy over here is doing something special. This is a Polymaster 1703 MO1B. This device is calculating dose for me right this moment. And if you want to, you can look right here and see the dose rate. Let me move this up here so you can see it. And it's going to be hard to see this, and I apologize. But currently, in microsieverts per hour, and this thing, by the way, is actually sensitive to the energy. It's not calibrated against energy like this. It's actually sensitive to it. So what this says in dose rate is actually pretty close to the real dose rate. It says that I'm receiving right now 0.06 microsieverts per hour. Let's reset this. Yeah, sure. Reset. Okay, this will show me my cumulative dose for this entire experience, and this is my dose rate, what it would be if I just left it for an hour. Okay, so sorry that's a little difficult to read, but I'll keep telling you every now and then what it says. All right, so let's start out with alpha radiation. Make sure you can read this. You know, it's too bad we can't just kind of get that cable back there and out of the way, right? Because that cable's in the way. There we go. Now you can see it. Okay, start with alpha radiation. An alpha particle is a particle emitted from an alpha particle emitting thing. Wow, that was circular. An alpha particle is made up of 2 protons. Those are positively charged. And 2 neutrons. Those are 0 neutrally charged. They actually do have an electrical charge. It's 0. Don't be confused with not having one. They have it. It's just 0. And I could explain what that means and why that's like that, but that's kind of complicated, so I'll get into that later. Well, not in this video, but in another one. Here is polonium-210. Polonium-210 decays via alpha decay. You notice the Geiger counter is not really noticing it. Nothing is really noticing it. There's a reason. Alpha particles don't travel very far in the air because they're so positively charged. Remember, 2 protons? That their electromagnetic field is they're so influenced by electromagnetic fields that they can't go very far. It's kind of like shooting a bullet into the woods. It doesn't really go very far because it hits all the trees. Kind of like that. Now, according to the NRC, the Nuclear Regulatory Commission, I can't take both of these and hold them against here at the same time. Stupid, huh? But apparently that's the rule. You can't use them together. But you can have them together. You can have a bunch of them. You just can't use them together, which is just stupid. But I'm sure they have some reason for that. So we'll use one. We'll take this guy right here. They're both exactly the same otherwise. But they decay pretty quickly. This one is from September of last year, so it's already decayed quite heavily. Let me get this really close to the lens and see if it'll pick it up. Can you see it? Now, I have a pretty good focus up close on this. Maybe we can see the polonium-210. Maybe not. But anyway, it's in the back of this little silver foil here, polonium-210 chloride. Now, we take the polonium-210, and as we move it closer, it is going to pick up a little bit more on this. And the reason for that is the polonium, every now and then an alpha actually makes it even this distance. Believe it or not, it can make it this distance, but barely. It's mostly X-rays being emitted from this. And I'll explain later on how X-rays are emitted randomly. And occasionally a gamma ray for that matter, but not very many. Notice as we get closer, nothing's really happening. Nothing amazing. And then suddenly, we get close enough, pull back, it stops. Close enough. Pull back, it stops. Crazy, huh? They don't really go very far, only about an inch. We get right up against the screen. Let's see what we get. 2,600 counts per minute. 35. Notice that my dose rate is only still at 0.07 microsieverts. Unchanged. Why do you think that is? Because the alpha particles aren't making it to the polymaster. 8,000. 9,000. 8,000. So about 8,000 counts a minute. It's decayed a lot. When I first got it in the mail, it was a lot faster than, or a lot more active than this. Now let me show an interesting property. Watch what happens when I put paper in between. Yes, that's right. Paper itself is capable of blocking alpha particles. Heck with lead, heck with anything else. Paper. Anything else, in fact, is good too. Lead or wood or paper or your hand. Anything will stop alpha particles. So it's not that paper is special. It's just that I'm showing that something as thin as paper is able to do it. Tissue paper, toilet paper, whatever. This happens to be a $100 billion note from Zimbabwe. In case you're curious, $100 billion from Zimbabwe before their economy crashed was enough to buy a loaf of bread. So don't get to any bright ideas. This isn't worth anything. It's just an interesting little piece. So we put this here, and you notice that we're picking up the alpha. We drop this in between. $100 billion worth of Zimbabwe shielding. Yes, sir. Pull it out. Put it in. Pull it out. Pull it in. Fun, huh? So let's put that back there. Now let's put this on the polymaster, see if it notices it up close. It's not really an alpha detector. It's not really alpha sensitive. There's actually an interesting way that it could potentially pick this up, but it's very doubtful. And it's not. It's completely blind to this. And that, by the way, is why these Geiger counters are still useful even with amazing tools like the polymaster. So I'd like to put 2 of them on there, but I can't do that because the NRC says bad. Okay, let's put that away. So that's alpha. Alpha radiation is what makes things like a uranium sample seem so incredibly radioactive, but if you put up the Geiger counter, the uranium piece goes crazy. But a lot of that is alpha. Get rid of the alpha, and it's less than half as radioactive as it seemed. So let's get rid of the alpha here. Let's switch to a different source. Let's switch to beta. Alright, for beta, I like to use strontium-90. Strontium-90 is a legal isotope. I'm allowed to own this, which is another reason it's nice to use. There are actually some other interesting beta emitters, but a lot of them produce gamma radiation too, and I wanted a reasonably pure beta emitter. I keep it in aluminum because aluminum is actually a really good thing to keep a pure beta emitter in. If you keep it in something like lead, and this also goes for alpha emitters too, you can actually produce more radiation or more penetrating radiation as a result of it. Interesting, huh? So let's pull this out. First off, let's see what it does when it goes near the polymaster. Polymaster is not picking it up. Geiger counter's not picking it up. So let's put it out. Let's open it up. That is a strontium-90 source. Let me see if you can see this. Strontium-90. See? Now, it's picked up from quite a distance away. Many feet. Notice the polymaster's not picking it up. And if you come at it from behind, it doesn't pick up at all. Wonder why that is. It's because betas are able to go a lot farther in the air, but they don't have the penetrating power that gammas do. They're even they're more penetrating than alphas, but less penetrating than gammas. Let's see what the polymaster does if I put this right on top. There it goes. It detects it on point blank. And I mean, it needs to be nearly point blank for it detected. It goes all the way up to 0.2, nearly 0.3 microsieverts per hour. And if we pull back just the tiniest little bit, the Polymaster barely detects it. In fact, that's it. It's done. It doesn't detect it anymore. Interesting. Now, let's see what we can use to block this. This is a piece of boron silicate glassware. See? Pyrex beaker, real thing. If we take this Pyrex beaker and we put the source in it and we put it near the Geiger counter, it blocks almost all of it. The same thing works with aluminum too. And for that matter, other thick things. Plastics do a pretty good job. But paper does almost nothing. Nothing. Let's see how high this gets. 73,000, 146,000, 148, 151. Let's say 156,000 counts per minute. Not bad. Strontium-90. Alright, so that's alpha, and then that's beta. Let's look at X-rays next. Now, some of you might find it interesting that I have X-rays. You might say, well, Tom, I already know. I've cheated. I've looked ahead. I know how you produce gamma rays. How do you produce just X-rays? With this. This is a tritium light. If you get really, 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 really dark, you can see it. See that? This tritium light source is actually a pure beta emitter. It does not produce any gammas or alphas or anything else. It produces pure beta only. In fact, there are only a few elements or isotopes like it that produce only pure beta. Anyhow, when that beta hits the plastic here, it causes a rapid slowdown of the beta particles, and the result of that are little X-rays that shoot off. They're called Bremsstrahlung radiation. I never pronounce that right because I'm not German, so I can't say German stuff correctly. But Bremsstrahlung. And basically put these little X-rays shoot off every direction. So this doesn't produce X-rays by itself, but in the plastic it does. Watch. Not much. But you notice the counts going up. Not much at all, but those are X-rays, just like you see at the doctor's office, except they have a hell of a lot more X-rays than you get from this, and they can project them at you in a pretty high intensity and much higher energy. We're up to 84 counts per minute, higher than our 30 plus normal background. Let's see what the Polymaster thinks and dose it. We're looking at 0.07. We'll dangle this over top of the Polymaster and see if it detects it. And then after this, we'll switch to gamma. There are X-rays coming out of that. But the X-rays are so low energy that they barely pick up on the Polymaster, whose threshold is anything above 40 kilo-electron volts. That's 40,000 electron volts. And the X-rays coming out of here might be that high, but they're probably actually a little bit lower than that. So, this is invisible to the Polymaster. Alright. Now, finally, Polymaster, I know you feel bad. The Geiger counter's been having all the fun, but you get some fun now because it's gamma rays, which you do the best with. Let's look at some gamma rays. Alrighty. Gamma rays. There we go. These two lead things have gamma ray sources underneath them. Look at that, the Polymaster's already going bananas just having them nearby. We're already at 0.2 microsieverts per hour. What could these two gamma sources be? Well, this thing can actually tell me which one each one is. In fact, let's let it do it. That might be fun just for giggles. Let's let the Polymaster tell us what they are. Let's put the Polymaster on top of this one. Do a quick identification. All right, go Polymaster, go. Tell us what is underneath, what is behind door number 1. Let's move this out of the way so it doesn't contaminate the sample. Now the Polymaster can actually tell us what's underneath these. And then after that I'll show you the gamma rays that come out of them. And the gamma rays that come out of them are what the Polymaster is reading right now to take a guess what this might be. Industrial cesium-137. Let's see if that's true. It is true. Go Polymaster, go. Cesium-137. Come on, focus. There it goes. Cesium-137. This produces beta and gamma. But if we put it behind the borosill, we'll be mostly picking up gamma. See? And picking up that gamma is much less than the beta it puts off. Right? But obviously, paper does nothing. Now, let's see if we can block the gamma coming out of this with a piece of lead. This looks like gold, but it's not. It's actually gold-painted lead. I painted it with the gold so I can handle it safely. Oh, that stops it. Nothing like lead. Now, technically speaking, if I get it close enough, you'll see that some of the gammas still make it through, but only a few. They go right through my hand. Actually, a lot of them get stuck in my hand, don't they? But still plenty enough to make them through. All right, so let's let the Polymaster take a guess at what the next one is. Quick identification. Let's move the second one over here. Go, Polymaster! Go, Polymaster, go! Go, Polymaster! Sounds like Pokemon, right? Go, Pokemon, go! Alright, that will tell us what the next one is. And then we're going to take the next one and put it under here and see it too. So these are gamma rays. Gamma rays are photons, just like the X-rays. In fact, a high-energy photon can be a gamma ray or an X-ray. The real difference, and they lied to you in school. You know how in school they said it was the energy, like lower level, high-energy photons, where X-rays and higher were gamma? It's not true. It's where they come from that makes a difference. Industrial cobalt-60. Yes, it is industrial cobalt-60. Thank you, Polymaster. I like saying that. I know it's sort of stupid, but come on. Come on. It's a nice camera, but like convincing its autofocus is a pain. Come on. Pick up the object that's close. Pick up close objects. Come on. Well, anyway, there it is. It's hard to see because it doesn't want to focus. But let's get back to our gamma measurement so we can see how much dose we've gotten so far. Probably a lot because I put this thing right on top of the actual sources. Come on, gamma measurement. Go, go, go. All right. As you can see, cobalt-60 picks up well. But you might be wondering, why is it that this source right here is actually picking up less than this source right here? The answer is this. The gamma rays coming out of this are so strong that they're going through this mostly without actually interacting with it. They can go right through the backside too, or this, or any other part. In fact, they can go through the Polymaster to get to the Geiger counter. But again, even though they're powerful, the lead stops them. But did you notice that they're going through the lead? Somewhat. This did not. It's because the gamma rays coming off of the cobalt-60 are stronger than the gamma rays coming off of the cesium-137. Amazing! So, we've had fun with alpha, beta, and gamma rays. And there are things that produce all of them, including X-rays, like this guy. This is a piece of uranium. And in fact, I probably don't need this, but you know, safety first. Wow, that didn't work. Well, decontamination second. Okay, Anyway, this is a piece of schlockingite. It's sort of ugly, but if you put it underneath a black light, it's okay. You know what? I give up. I will decontaminate afterwards. This just isn't happening. Look at that. Beautiful, beautiful specimen. All right, beautiful specimen. Using the other hand. Let's see if any of it is alpha. A lot of it is alpha, but crap, touching everything with my hand. But it's hard to show you with this. But I will show you that a lot of it is beta. And I'll show you that the rest of it is gamma. All right. And if that's not enough fun, if that's just not enough for you, then we have the ultimate last thing, the quantum pendant. I love these things. My favorite check source. Go, quantum pendant, go! When I saw this, I realized that this would be my favorite nuclear check source. The quantum pendant has alpha, beta, and gamma radiation as well. Alright, so there has been our little demonstration. This is Tom from anti-proton.com, and bye-bye. Okay, let's take out the pickle probe, open up the beta shield, set this to times 100, release the hounds. Beta source. $15,000 counts per minute. 10,000. There we go, sweet spot. 25,000 counts per minute. Yeah, buddy.